APR of 15%. APR of 15%. So what is the percent increase per year if there's an APR of 15%? There's an APR of 15%. What is the percent increase per year? What's that? 115%. What's that? 15%. Is that what APR of 15% means? Okay, so here's the deal. Just saying APR 15%, you don't know. Because APR is this kind of weird percent. It's different. It's different than all the ones we've been talking about before in that you also need to know how many times throughout the year you're going to take the interest and put it back into the account. That's called compounding. So depending on how you compound, an APR of 15% will have different results. So APR is like a different beast than everything we've done up to this point in the exponential growth. So what we do is we start with, we're going to do quarterly compounding, and right off the bat, we say that the per period rate is we take that 15%, so 0.15, and we do what we said we can't do. We divide it by 4 to get the quarterly rates, the quarterly increase. Now, once you do that, now you have a true increase. This is truly the percent gain of your money every quarter. Okay, so let's calculate that. So that equals 0.15 divided by this here, number of compoundings per year, which is 4. Okay, so what percent does your money increase every quarter if you have 15% compounded quarterly? Then what percent increase do we have? Is that the true increase? This is the true increase, okay? Once you do that first division, now we've got something to work with. Now everything from here on out follows what we learned about exponential growth, okay? If you've got so what is the per period growth factor? Zach Wilden. Where's Zach? Yeah. I called you last time. Adam, you're next. If 0.0375 is the per period rate, what's the per period or the quarterly growth factor?
Would that be 1.0375?
So, and how'd you get that? So explicitly, you did 1 plus this number that we calculated, right? Yeah. So we're just going to add 1 to that, right? We've got the percent increase as a decimal already, and we know that to get our growth factor from our decimal version, we just add 1 to get that growth factor. So equals, that should feel comfortable, 1 plus this. Are we good so far? So now we got the quarterly growth factor. How do we get the annual growth factor? So over the course of the year, what one multiplier would be equivalent to this quarterly multiplier over the course of a year? Cujo. You take that to the 4th power. He said times that together 4 times to get the annual growth factor. That's it. So the number is important, but what's more important is this process. So it's going to be that number, 1 plus 0.15 over 4. And you want to do what? Take it to the 4th. And we just got the annual growth factor. So we can get the number now. So it's going to be equals that thing to the number of compoundings per year. E6 to the A6. How much does our money increase every year? How much, by what percent does our money increase every year? 15.87, you see? Not 15%. This is called the APY. Oops, what happened? I want this. This is called the APY versus the APC. I know what both of these things mean. The APR is this number that's no good without knowing how often you compound. So APR requires this additional information of how many times you compound per year. APY then is the true annual percent increase. So the APY in this case is? You told me 15.87%. So when you do 15% APR with quarterly compounding, your result at the end of the year is that your increase is 15.87%. And why is that? Why is it more than 15%? Where does that extra little increase come from? So we should know that, the general principle of that. Okay? Yeah, so now we're doing this multiplication 4 times, certainly. So can anyone be more specific than that? That's true?
It's due to the fact that you are compounding it over and over again, depending on whether it's quarterly or however many times. The percent is going to increase very slightly if you compound it more often.
And why? Yeah, so it's because of compounding. What is compounding? Why does this result in a higher percent increase? That's right? Yeah.
What you already had money again, which you're times your growth factor, and you're adding it to itself, and you're measuring it again. So the same measurement again based on growth factor.
Right. So when you compound, you take the interest earned so far and you put it back into the account. Now you have a higher amount, right? So now you have this higher amount by which you're going to take the percent increase. So it's like you get percent on the percent, right? You take the percent after 1 quarter, now you put it in, and after 2 quarters, that second quarter will get a greater increase because we have the percent from the first quarter. Okay? That's what compounding is. So yeah, you guys all got it. All right, so now we want the T-year growth factor. This is the annual growth factor. We want a growth factor for T years. What would that be? Patrick?
Just say the 1 plus 0.15 before.
Okay.
And raise it to the T power.
So you want to take the annual growth factor, and you want to raise it to the T power is what I heard. Yep, so we're going to take that thing to the 4, and now we're going to take that annual growth factor and multiply it together, T times, and we'll get the T-year growth factor. What does a T-year growth factor do? What does it mean? So what will that do? Moises?
It tells you how many years you're actually do that for. Altogether.
How many years? Okay. So in a calculation, what would it mean in a calculation? What does it do for us mathematically? If it's a growth factor, right? What's a growth factor?
Put it into another function.
Put it into another function. What's a growth factor? It's a multiplier. What will it help us multiply to get? Right. So our output is like how much money we have. So if we start with $6,000, value of $6,000 initially, and we multiply it by this, what will the result be? So we have this output of 6,000. We're going to multiply it by the T-year growth factor. What will it mean? So I'm going to take 6,000 times the T-year growth factor. Does it make sense to do that? And what will the result be? He wants the amount of money after 2 years. So I just took my 6,000 times the T-year growth factor. Yeah, so the old output was what we started with, 6,000. So the new output will be what he said. It'll be the new amount T years later, right? So it's the new output T years later. if we start with 6,000? Okay, any questions on, so the numbers are easy. The numbers are pretty easy to work with, but what I've written by hand is kind of the most important part, is really understanding all those expressions and how we're building this up. And in the end, if we have a starting value, now we can easily figure out how much that's going to be worth in T years by multiplying by the T-year growth factor. Okay, so what I want you to do is I want you to work through these for 12 months in a year, 52 weeks in a year, and 365 days in a year. And you're going to see that the APY is going to be different. You're going to get different APY every time. That's why just having APR of 15% by itself is not good enough. You got to know also what's your compounding scheme, because you'll get a different APY each time. So again, the focus is on what I've written by hand. What I've written by hand is really the most important thing to be practicing. Numbers, if you get that, the numbers come easily, okay? So you can work on those three, and I'm going to take roll. Gotcha. Are we still in scrunched version? Does it look like this? You can read it? When we get to trig and we do circles, this will not do. We need real circles. Okay, did you get these for the monthly numbers? Is that right? Okay, what is our increase per year with monthly compounding? He wants 16.08%. What do you think? That's it. The APY, this gives an APY of 16.08%. So notice, so an APR of 15% means nothing unless you know what your compounding is, because it's different for different compounding. Okay? So the value of 6,000 after T years. So I'm not going to write all that in, but let's just do this. So how would I get the value of 6,000 after T years with monthly compounding? Gage, you're up. Did you get it?
For the last part?
Yep.
6,000
6,000.
times 1 plus 0.15 divided by 12.
And how about just that? What's the 1 plus 0.15 divided by 12? What does that mean?
That is the annual growth factor, or that would be the period growth factor.
And our period is?
It's 1.0125.
Okay, so it's a 1 month growth factor. Okay, keep going.
And then you would do that to the 12 for 12 months, and then you do that to the T for the years.
Right. So in that formula right there, for the value of 6,000 after T years, how many growth factors are there? How many growth factors can you see in that? He said 2. What's the first one we have? The first growth factor is right there. Which growth factor is that? Monthly growth factor. It's what you would multiply your money by to get the amount of money after 1 month. What's the next one we got? Annual. It's what you'd multiply your money by to get how much you'd have in 1 year. That's your multiplier for the money 1 year out. And then we got another one. What's that? That's another growth factor. The T-year growth factor. Which one of them gets us the APY? Blue, red, or black? The red one, the annual growth factor, that multiplier for annual, is our 1.1608. Helps us get what the percent increase is per year. All right, so for those of you who want to get the numbers here. Okay, so did you get an annual growth factor of 1.1616 for weekly? And then daily 1.1618. So what happens when you compound more often? So you can compare the APY is what you want to compare in terms of the yield or the effect of this investment is like the APY. What are you noticing with more compounding? You get a higher rate. So this APY is 16.16, and then daily 16.18. So the more often that we take the interest, put it back into the account so that the interest can build on interest, the more often we do that, the better the results if we're the investor here, right? The better the results if we're the investor. Now, does that mean that the more often you do it, that your percent increase just goes off to infinity? What's happening? It's increasing, but it's slowing down, right? It's like leveling off, right? It's increasing, but the more often we do it, it's not like we just get this infinite percent increase. It starts to level off. It starts to level off, and it's like approaching some value. Question, Adam?
I was going to ask, well, why is it like our gap between quarterly and monthly we have kind of was it like a 0.003? We have like kind of a substantial gap.
Right.
Like 12 to 365 is almost is 0.001.
Right. So the biggest jump is from just if it was 15% per year to quarterly, almost a whole percent. And then if you go from quarterly to monthly, you're right. Now it's only going up like a quarter of a percent. So that's the idea that as you compound more often, it's better, but the returns aren't as great, right? So the reason that is, it's because just the idea of compounding or the execution of compounding is helpful, but the more that you do it, that's a longer answer. So the answer to your question is it takes more investigation as to why do the increases decrease. That's what you're asking, right? Yeah, that's a more complicated question. But the biggest effect is when you just start compounding in general. So doing quarterly or monthly, that's when you get your best jump. But then doing it weekly or daily doesn't help that much more. Okay, other questions? All right, so we'll come back to this idea of what the APY leveling off. We'll come back to that in a second. But what we want to do now is let's do it totally in general. So your APR is any number R, N compoundings per year, initial investment of P. Same process. So work it out. Same process. We want to work out, get the per period rate, the per period growth factor, the annual growth factor, the T-year growth factor, and the value of P dollars after T years. So now it's just everything is in general. So what are we doing? We're building a formula. But it's the same thing we did before. Work together. Jackson, did you get it? You're up. Per period rate. How do we get the per period rate?
Divide R by N.
He wants R divided by N. And is that a true rate of increase per period or something else? He's saying it's a true rate of increase per period. Is that right? Yep. Right. We do that first because based on this one, now we can apply everything we've learned about exponential growth without exceptions, right? So now everything is built off the per period rate. All right? You're doing good. Keep going. What's the per period growth factor?
Per period growth factor, you would add that to 1.
He wants 1 plus R over N. Yep. All right. Keep going.
So for your annual growth factor, you take R plus, or you take R over N plus 1, and you take that to the nth power.
Why?
Because that's how many sections or periods you have for your compounding sections. So you have to take that to your power of y.
You're going to multiply that per period growth factor together that many times to make up a year, right? So n times in a year, you're going to multiply that per period growth factor times itself n times. How do we get the APY from that?
You multiply that by p.
He wants to multiply that by p to get the APY. What do you think? She said, so Na said you get the answer and then
you just
take away the 1. So Angelica, same thing? Yeah, so you're going to take that thing and you're going to take away the 1. Well, mathematically, what is that? Subtract 1, right? And then turn into a percent. That's what you're doing by looking at it, right? 1.13. You're saying, oh, it's 13% increase. Well, mathematically, what are you doing? You're subtracting 1 and multiplying by 100. Okay? T-year growth factor. Let's go with somebody new. So Ryan. No. Yeah, Ryan. Sorry.
So the percentage.
T-year growth factor.
We would take what you have before, so the 1 plus R over N to the N power.
Yep.
And you take that to the whole thing to the T power.
Why?
Because that's how many years that you're figuring out.
Yeah.
For your growth factor. So you take what you have before and to whatever years that you want to finish, which is T.
Right. What is taking it to the T? What is it telling us to do? Take the 1-year growth factor and what? Nathan. Multiply it together, T times. Every year that goes by, you multiply by the annual growth factor. So in T years, you're going to multiply it by the annual growth factor T times. That's why we raise it to the T. Okay, value of P dollars. So now what we have is we have a function of the number of years, and this is the final value after T years, final value of our investment. After 2 years. It's a function. So we've got the T-year growth factor, and we start with P dollars. How much will we have after 2 years? Taylor.
2 years, it is, you take the entire T-year growth factor and multiply that by P.
Yeah. So we're going to take the starting output, right? And multiply it by the T-year growth factor, and that'll get us the output 2 years later. Okay? Many of you have used this formula in the past, and you may or may not, I guess most likely you did not, understood that it was all about growth factors. And now we know what every part of that is about, right? You start with your per period rate, you get your per period growth factor, get your annual growth factor, get your T-year growth factor, and then multiply it. It's a multiplier, so we multiply it by P. Okay, so this is our compound interest formula. So not only should you be able to use it, that's the easy part, but we've taken a half an hour to build this thing and understand where it all comes from. So you will be tested on that. You're tested on your understanding of what's going on there in that formula, where it comes from. Questions? Okay, so let's go back to what happened to the APY each time. APY increased. So the APY, so APY. 15.87 for quarterly compounding. 16.08 for monthly. 16.16 for weekly. And 16.18. So what's the best we could do in terms of compounding? We keep getting a slightly better and better result here as we compound more and more often. Theoretically, what's the best that we could do in terms of how often we compound? Yeah.
Could we go per second?
Yeah, per second, okay? Can we do better than that? Millisecond.
We can go exponentially. Or wait, no, not exponentially. We can go, oh my gosh. Yeah,
Just what's the idea of it? You're trying to think of a word, but what's the idea of it?
Infinitely.
Every moment, right? So it's basically like seconds or milliseconds or microseconds or whatever. But every moment. So if we could compound every single moment, that would be the best we could do for an APR of 15%, right? That'd be the best we can do. Okay, this is called continuous compounding. Is that the word you're looking for?
Yes.
Continuous compounding. All right, that's like compounding every moment.
Is that the same as negative infinity?
Right. So in our formula, so we have our formula here. Oh no. There we go. Okay, so we got our output was equal to P times 1 plus R over N to the N to the T. So what would change? What would we have for continuous compounding in this formula? What would that represent? So would you say, Nas?
Negative infinity?
Negative infinity?
Yeah.
So which symbol changes here?
Instead of the compound, which is
Yeah, this is our N value. So what would N be?
minus infinity.
I don't know why I'm saying minus infinity. We're going 4, 12, 52. These are all positive values, right?
Yeah.
So
Infinity, right?
yeah, just infinity. So we want N to go to infinity, okay? In this formula, that would represent continuous compounding if we could let N go to infinity. But that's problematic because, what number is that? How do you divide by infinity? How do you raise a number to the infinity? Fernando's dying to say something.
Well, I mean, it would just be what would change would be your growth factor. You would still have the principal, you would still have the amount of years you compounded for, but your growth factor would just change to E since you go to infinity.
Well, okay, so you remember that, okay? You remember that, but so he's right. So for continuous growth, continuous compounding, I should say. He's saying that what stays the same? Our initial amount stays the same, and T stays the same, but something's different here. So this 1 plus R over N to the N is problematic if N is infinity, or N is going to infinity. You can't divide by infinity, you can't raise something to the infinity. So it requires a little bit more advanced mathematics. If you want to talk about that outside of class, I'm happy to. But we're not going to take the time to kind of derive that. But what happens is, as you let N goes to infinity, what you get for this annual growth factor, right? Inside those brackets, there's the annual growth factor. You get E to the R. So R is the APR. More generally, it's called the continuous rate. Is the continuous rate the amount our money increases over the year? Is the continuous rate the amount of increase of our money over the year? No, because it's like the APR, okay? It's like this R, this continuous rate thing, this is hard for students to get. It's like on the exams, you're going to get really low success on this continuous stuff. So try to really work hard at it. Okay, the continuous rate is like an APR. It's not the true percent increase per unit. You've got to do something else to get it. So what are you going to do? So what is e to the r? E to the r then is, what is the meaning of e to the r? What's the meaning of it, though? So that e to the r is equivalent to, for a continuous, is equivalent to all that stuff that I've put in red. So what is the meaning of e to the r?
Continuous compounding.
Is it a percent increase or a growth factor? It's a growth factor. Which growth factor is it? Annual, or the 1 unit. Go ahead.
It's the annual growth factor as n approaches infinity.
That's right, exactly. It's the annual growth factor as n goes to infinity, or continuous compounding. Okay? So e to the r is the annual growth factor. Is that a true growth factor or something else? That's a true growth factor, just like in the box. It's the true annual growth factor. So R, the continuous rate, is like APR. It does not reflect actual precise percent increase. But e to the r can help us get that, because e to the r is still the annual growth factor. Oh, and so what is e? We never talk about e. E is called the natural base. 2.8281828459045, and on and on. I didn't memorize very many of them, because there's an infinite number of decimal places, so I didn't hardly memorize any of them. Just enough to get by, exactly. So, but the point is, so, what do you think math teachers do in their spare time? Memorize stuff, right? No, I'm kidding. No, so the point is that E is a constant number. It's a constant. It's always the same number. It's called the natural base. The natural base. It is right. It's a number just like the type of number pi is. It's an irrational, non-repeating, or non-repeating infinitesimal. That's right. It's a number like pi, and it comes into this. It comes in when we say, all right, we want to compound every single moment. We want to compound every single moment. The mathematics builds this number e. Yeah, question.
So what if n is equal to 1?
N is equal to 1. Then you just get 15% per year.
So is this true?
Yeah, then it would be true. If n is 1, then you're truly increasing by 15% per year. But normally it's not. Normally, when you talk about APR, you have some kind of compounding. Yeah. Okay, so what I want you to find is, can you find the actual, so in your calculator, TI on the left, over on the left side, you go second ln on the TI. It'll give you E, and that's that number E, and then a caret, so it's waiting for your exponent, right? Because E is normally raised to a power, so it's waiting for the exponent. So we want to find out what's the APY with continuous compounding. So we're going to do E to the what? And what is our R? 0.15. You're going to do e to the 0.15, and that's going to give us, is that going to give us a percent increase? No, it'll give us annual growth factor. Okay, so e to the 0.15 should be 0.1618 what? So it's a 1. It's 1, right? 1.16183. Is that right? So therefore, that is the true growth factor for continuous compounding. It's the same as what I put in red if we had finite number of compounds. Same type of number. So from that, we can get the true yield. APY is 16.183. So virtually no difference, just a little bit more than a daily compounding. But it's the very best that we can do is continuous compounding given a certain APR. Okay, questions on this? So we'll be doing some examples, but this is kind of tricky. You really got to keep your stuff straight. The continuous rate is not the precise amount of increase. You have to combine it with compounding to figure out what the true increase is. And the way you do that is you do e to the r gives you the corresponding growth factor from which you can get the true percent increase. Adam.
So I know with this example, it comes out pretty close. But since e is just 2.78, it's always that same number.
Yep.
Would it be off, or would it still be that close?
If you have a larger APR, like if you started with 30%, then you have a bigger difference in the different compounds. Like the bigger your APR is, the more drastic these changes are as you compound more. Does that answer it? So if you have a small, if like your APR was 1%, the original APR was 1%, then compounding will have very little effect. And so there would be almost no difference at all between daily and continuous if you had a very small APR to start with. Does that kind of help? Nice.
So does that mean like the APY program, the compounding is infinity?
Yeah, what we call continuous compounding. Compounding every moment.
Okay.
Every moment, or continuous compounding.
How come it's like close to the daily one? So I have to do this by seconds.
Yeah, that's the same question you asked before. Because we'd have to dig in more into the mathematics of it. But daily is virtually every moment. Like there's just hardly any difference. Whereas the difference between quarterly and monthly is a much bigger difference. But the reason why it takes more time to talk about. Yeah. But just know that you have these decreasing returns, right? So the more you compound, yeah, it gets higher, but by less and less and less and less. Yep. Other questions? Okay, so let's look at an example. Yeah.
Are you finding the value you know how you said like R over N plus 1 that's into
R over N plus 1, that's your per period growth factor.
how do you find when you come back
To the N, this. The only thing that's not an actual percent increase is the APR of 15%. Every other percent increase that we found per period, per annual, those are all actual percent increases. The only one that's not is the APR. So same thing with continuous. This continuous rate is just like APR. It's not reflective of the compounding. So this combines it with the compounding, and that's e to the r then is your annual growth factor. And so the annual growth factor 1.16183, therefore the true rate of increase 16.183%. Is it better? Okay. So let's look at an example of decay. So now this idea of continuous compounding, we can really model now, we can kind of go, it's like come full circle, and we can model all exponential growth a new way now as continuous growth. Okay, so any type of decay or exponential growth, now we can also model it in this new way, where R is the continuous rate. That's not your class. Why is it? There it is. Okay. Sorry, wasn't ready. Here we go. So here's an example. So it's not an investment anymore. Oh jeez. Pause. Oh god. There we go. Okay. So now it's not investment anymore. It's this profits. Okay. It's profits and it's decay. So when we come to this function right here, we have to see it as P times okay. All right, we got to see it as P times. Why? There we go. I don't understand. Where am I? Anyway, so just imagine here, this is P times E to the R M, okay? So what does this indicate, right? This number right here, negative 0.0412. That's R, okay? So that is the continuous decay rate. Does it mean that we're decreasing by 1.42% every unit? No, it's a continuous rate. It's like an APR. It doesn't reflect the true decrease. So how are we going to get the true decrease? You know, you're going to do this. Say, you're going to do this. How are you going to get the true decrease? Find out what that is. So calculate E to the R. And get that. Maybe I can get this to work. Okay, 0.9. What is that? That is the per unit decay factor. What does it represent? It represents the amount, what? Which amount? The amount that we keep, actually, right? So this is an actual decay factor. E to the R is an actual decay factor, so it's the amount that we keep. How do we get the true percent decrease then? Who's got it? What is it? 1.4. One more decimal place. Like this? So notice, for a continuous decay rate of 1.42, the true rate of decay per unit is 1.409%. That comes from getting that per unit decay factor first. The continuous rate does not give you the true change. Homework due Wednesday. What? Usually end of the day.